So, next question. Let's get rid of all this up here. Grab all that. It says, students investigate terminal speed for falling paper cases. State what is meant by terminal speed. Well, the terminal speed is pretty much the maximum speed our object can do when the forces are balanced, when there's no resultant force. If you're falling through the air, I think we looked up the other day, you need to be falling more than 450 meters to reach terminal velocity for a human body. So that's at the point at which you stop accelerating and you just fall in then, where air resistance is balanced with your weight. Describe how you'd carry out the investigation. So it's worth 6 marks. I've put them in bullet points, but obviously when you come to do this, I mean, because it's a method, bullet points might get you the marks. So I would probably lay it out like this. This is how I would lay it out. So I've said set the pointer to the required distance above the ground. For example, 150 centimeters above the floor. Okay, so that's the first thing you do. So this thing by here, the pointer, is the point at which you start measuring. You start that timer. Use a balance to determine the mass of the cake case. So you could weigh 10 cake cases, and you could divide it by 10 to get one, or you could do one at a time. Drop a single case from a chosen height, for example, 20 centimeters above the pointer to allow it to reach terminal velocity. This is the most important bit. We're not dropping from here because we're timing from here. This cake case needs to reach terminal velocity by the time it hits this. And then we start the timer, and then we stop it as it hits the floor. Okay? So we're assuming, we're seeing how mass affects the terminal, the speed of terminal velocity. Use a stopwatch to record the time it takes for it to fall to the floor. Repeat a number of times, say like 5 times, to calculate the mean. This then gives us a more accurate result, and it reduces the anomalous effect because we're going to get anomalies in this. Repeat the process with different numbers of cake cases. For example, you use 2 cake cases, then 3, then 4 and 5, and you record into a suitable table. And then you would use speed equals distance over time to calculate the speed. And that's that one. Oh, I might need to keep that out. So where is that? The table shows the results from the investigation. So let me just pop this down by here. Complete the table using an equation on page 2 to find the missing values. So what do we know? We know the distance. We know, there's the distance. And we also need the time. Mean time, sorry. This is the time, this is the distance. I don't know what I'm on about there. So it was always 1.5 meters above the ground. And then for this one, it was 0.6 seconds it took to fall. It's naughty there because you see that meters, but it's in seconds. Time to fall 1.5 meters. So I got confused there. It comes out to be 2.5. We're going to plot these results now. You're already given the axes and the labels. So it's just accuracy in plotting. You can see my curve is slightly off there. I need to bring my curve right up. But I did it in pen, and I don't get another chance. This is why it's so important to do in pencil. And then one student suggests that doubling the number of cake cases reduces the time to do it fall by half. Explain whether the results support the suggestions. For 3 marks now, I'm going to do a little bit of trial and error. I'm going to say one case, it takes 0.9 seconds. Where did I get that information? I got it from here, look. Okay? So if it takes 0.9 seconds, 2 cases take 0.68 seconds. Well, 0.68 is not half of 0.9. Therefore, this statement is incorrect already. I'll try it with 4 cases. Does it double? Does it double? No, it doesn't. Okay? It's not half at all. It's nowhere near. And you can see that this statement here, you would need a straight line going up. Okay? It needs to be proportional. You can see from the line that it's not proportional at all. This is increasing at a decreasing rate. The statement's incorrect there. How many more have I got? I may be able to do this in one video now. A skydiver of a mass 60 kilograms and weighs 600 newtons. The diagram below shows the forces acting on the skydiver at one point in her fall. Calculate the resultant force. So the resultant force, remember, we're not asked to use an equation. So I've got air resistance at 150. I've got a weight at 600. The resultant force is going to be this one minus this one, which is 450 newtons. Calculate the acceleration. It's given us the equation, but it's going to be F equals ma. So it's 450, her resultant force over her mass, which was 60, and it's 7.5. Describe how the force is acting on the skydiver. Alter her motion just after jumping from the plane to the point of reaching terminal velocity. So this is a nice little question. 6 marker, likely to come up as a 6 marker. So initially, when she first jumps out, the only force is acting on the skydiver is weight, because there's no air resistance. So the arrow is just going to be pointing down at still 600 newtons. This will never change. Her mass will always be 60, sorry. Therefore, gravity is usually 10 newtons per kilogram. So, but there's not going to be any arrow here when she first jumped out. So this makes her accelerate at a maximum of 10 meters per second. So that is pretty much the acceleration due to gravity, 10 meters per second. As her speed increases, the air resistance acting upwards increases and her resultant force decreases. So what that means is this doesn't decrease, but as this increases, makes her resultant force decrease, because obviously resultant force is the big one. Take away the little one. Her downward acceleration decreases because she's going to stop accelerating. Doesn't mean she stopped moving. Her downward force acceleration decreases until the resultant force becomes 0, and this is the point where terminal velocity is reached. Okay, the skydiver will eventually reach terminal speed where her weight is equal to air resistance and the forces become 0 or balanced. 2 more pages. This is a big paper, this one. In a class experiment, a group of students use a force to accelerate a vehicle along a frictionless air track. So we've got a set of results here. Let's plot them. So it's given us our axes. We don't have to worry about that. So we're all about the accuracy of our plotting. Just check. Always check your scale. So each box here is worth 0.5. Each box here is worth... each box here is worth 1. Each box here is worth going to be 0.5, 1. No, it's not. So that's 1. It's going to be 0.2, isn't it? Sorry. Bit of a brain moment there. Yeah, just check. Always check your scale. So I've plotted those results. That's in red. We can also see an anomalous result, which they've given us, which I've just circled. So don't ever join the lines up. Okay, I don't want to ever see that. In physics, you're either doing a straight line of best fit or you're doing a curve. So we don't want to see that. And then we've probably got some questions. Stick that up there. And this thing. Let's keep that there. And then we've got use a graph to find the force that produces an acceleration of 2.0 meters per second. So let's have a look at acceleration of 2 meters per second. The force is going to be 5. So 5 newtons there. Use an equation, mass equals resultant force over acceleration, so that's FMA, to calculate the mass of the vehicle. So when I rearrange, well, it's already done for you, but so F over A, which is 5 over 2, because the acceleration was 2 there. Another group of students in the class carry out the same experiment, but they use a vehicle with a greater mass. Now, I don't know if you remember me saying earlier, but if it's got more mass, it's going to be less acceleration. Because, and I can even prove that to you, if we increase this from 2 to 3, there's going to be less, so 1.6. So acceleration is going to decrease. Therefore, the line underneath the graph is going to be less steep. So for the same amount of force, you're going to get less acceleration because you've got more mass, you're heavier. And then Eric suggests that a force of 60 newtons is applied to the original vehicle. The acceleration will be 5.6. Use the data to consider whether this suggestion is correct. So we're literally picking out that formula again, F equals ma. We're looking for the acceleration because if a force of 16 newtons is applied, we know that. the acceleration will be 5.6. Well, let's have a look what the acceleration will be. So I've got 16 over the 2.5, which is my mass. It's going to be 6.4 meters per second, which is not 5.6. So it's not equal to 5.6. You could have also got that from the graph as well, but this statement is incorrect. And that's that paper. Lovely.